Hello, welcome back. So in this video, we're going to go ahead and try and solve matrix equations. In the previous video, link at the top of the screen if you haven't saw it already, I went over how we can perform matrix operations. Now, using these matrix operations, we can create matrix equations, something like this, and we can attempt to solve them. Over here, I've given you three matrices, A, X, and B. And using these matrices, I've constructed a matrix equation, which is AX is equal to B, and I've written down the same equation over here. Now, what I want to try and do is solve this matrix equation for X over here. Now, you might have no idea how to do this, so I recommend to start the problem by performing matrix operation on A and X. Once again, if you're not familiar with matrix multiplication, go ahead to the previous video and check that out where I teach you how to multiply matrices. But once you can perform matrix operation, you can go ahead and perform matrix operation on A and X and equate the rows of the new matrix you get to the rows of B. That should be a good starting point. So go ahead, pause the video, see if you can perform matrix operation on A and X and equate it to the rows of B and see what you get. Because I promise you, it would look a lot similar to something we've done previously once you do that. So perform the matrix operation and come back when you're ready.
So before watching this video, you should know that I plan to make videos covering the entire undergraduate linear algebra curriculum. So make sure that you subscribe to my channel and turn notifications on, and you'll know when I post a new video that will correspond with the concepts you're covering in class. Also, I plan on making review videos that cover these topics at a faster pace. Check my channel if I've released those already, because that will be useful to you if you already know this concept and you don't have to sit around with a more in-depth explanation. And you should get the content across faster. Okay, cool. With that, let's get back into the video.
Alright, so assuming you perform the matrix multiplication, you should get the following system. So I'm going to go ahead and do the multiplication now. You can skip ahead if you've already done it, but I'm just going to do it now in case anyone hasn't gotten it that watched the previous video already. Okay, so here we have a column matrix, and here we have a matrix that has 2 rows and 3 columns. So the first thing I want to do is just prove to you that yes, we can actually do matrix multiplication in the first place. So this over here, since it has 2 rows and 3 columns, is a 2 by 3 matrix. This over here, since it has 3 rows and 1 column, is a 3 by 1 matrix. Since the columns of this matrix and the rows of this matrix are equal, we can in fact perform matrix multiplication. Furthermore, we can also determine that the resulting matrix is going to be 2 by 1, because we can cross these out and the remaining quantities are 2 and 1, so we're going to have a 2 by 1 matrix as the resulting matrix of our multiplication. And that's important because the matrix that we're equating it to is also 2 by 1. So if both of the matrices weren't 2 by 1, then this would be impossible. But since they are, we can go ahead and actually solve the matrix equation. Okay, so now let's go ahead and actually do the multiplications. Remember, it's row by column. So 1x1, I'm just going to write x1, plus, minus 2x2 plus x3 is going to be, well, we're multiplying the first row by the first column, so it's going to be row 1, column 1 in a resulting matrix. Now we can go ahead and multiply row 2 by column 1 to get the first column, the second row of a resulting matrix. It's only going to have one column, as we can see from this size right here, but we're going to multiply row 2 by column 1 to get the second row of our matrix. So it's going to be 2x1, because we need to multiply the first entry of the first row by the first entry of the column, plus now the second entry of the second row by the second entry of the column, so 3x2 minus the third entry of the third row by the third entry in the column, minus 2x3. So this is the resulting matrix of our matrix multiplication, and this is going to equal 0, 0. Now, the reason that I said that this should look familiar to you is because here all we have is a system of equations. Because in order to solve this matrix equation, each row of this matrix, of the matrix AX, has to equal each row of the resulting matrix. So we can just write out all of the equations and what the equations equal in terms of the rows of B. So x1 minus 2x2 plus x3 should equal, well, that's the first row of ax, so it should equal the first row of b, so it should equal 0. Now we'll have 2x1 plus 3x2 minus 2x3 is equal to 0 because row 2 of ax has to equal row 2 of b. At this point, you should be able to solve this system because it's just a system of equations like we've dealt with before. If you're not really sure on how to approach this system, I've linked a video of mine where I go ahead and teach you how to do this in the top corner of the screen, but I'm going to go ahead and use a calculator now to solve the system for x1, x2, and x3. But before we do that, actually, I wanted to show you one thing. Here, if you notice, and this is pretty cool because this is some terminology we've seen before, we have all of our constants being equal to 0 in the system of equations. This is interesting because here, if we have all zeros in our system of equations, we're left with an homogeneous system of equations. If you don't know what that is, then I'm sorry that I'm doing this so much, but there's really a lot of concepts that we've learned to build up to this, so it's important that you know everything before we move on. But you should see one of my other videos at the top of the screen where I go over homogeneous systems of equations, and it's important that you know homogeneous systems of equations for the conclusion I'm going to get to next. But yeah, this is a homogeneous system of equations because, well, all the constants are equal to 0. So in a homogeneous system of equations, if you recall, there are two cases. The first case is that there's only one solution, which is the trivial solution, and the second case is that there are infinite solutions. And in fact, here we can already tell that there's going to be infinite solutions because there's more variables than equations. Once again, go ahead and watch my video on homogeneous equations if that doesn't make sense to you. But if there's more variables than equations in a homogeneous system of equations, then we can determine that there's going to be infinite solutions. So now that we have this, to solve the system, I'm just going to go ahead and construct my augmented matrix. So my coefficient matrix, which is this right here, augmented with the constant matrix over here. So once again, A is just my coefficient matrix, and B is going to be the augmented matrix. I went ahead and wrote out the system here so you could see how it actually works out, but that's not necessarily, you don't have to necessarily do that all the time. In fact, I'm going to go back in a second and show you how you could just got the augmented matrix immediately without doing all of these extra steps. But for the sake of demonstration, I'm showing you that you can actually see that AX is equal to B will give you a system of equations and how we arrived at that system of equations. We just equated the rows. But I'll just go back and show you that they're the same thing. Okay, so here we can go ahead and create an augmented matrix like we've done before when we've been given a system of equations like this. So the first column is going to have coefficients of x1, second column is going to have coefficients of x2, third column is going to have coefficients of x3. So the coefficients of x1 are 1 and 2, coefficients of x2 are minus 2 and 3, and the coefficients of x3 are 1 and minus 2. And we can add on a column of zeros because those are the constants. So this is the augmented matrix of our system of equations. So if you notice something here, all that we really did was take A and augment it to B. So if we just added B onto A, we would have got the exact same matrix. You might represent that as this, because we're just taking A and we're adding on a column of B, because that's exactly what our augmented matrix is. B contains the constant terms and A contains the coefficients. A is just the coefficient matrix of our system of equations. So I think that that's something that's worth noting and could save us a lot of time if you're in like an exam or a homework where you didn't want to write out all these steps. But I just wrote out all these steps to show you that once we actually perform the matrix multiplication, you will get this exact same system of equations. And using what we already know, we can turn that system of equations into a matrix. Okay? Cool. So we have this system of equations. Once again, we're going to solve it. If you don't know how to solve, you're probably extremely lost right now. So go ahead and watch my video on solving systems of equations, but I'm going to use a calculator here. We can go ahead and do row reduced echelon form. Okay, so we can find the row-reduced echelon form of this matrix, and that should hopefully give us the infinite solutions, because there's more variables than equations. We're going to have infinite solutions to this homogeneous system of equations. And using those infinite solutions, I'll show you how we can represent the solutions in terms of the matrix equation. So let's go ahead and find the row-reduced echelon form of this matrix. Once we do that, we should get, so the first column once again represents x1. We'll get 1, 0. The second column represents x2, so 0, 1. Third column represents x3, so minus 1 over 7, minus 4 over 7. And here we can add on a column with the solutions, or the constants, so 0, 0. So this is the solutions to our system of equations, and, well, we can find the solutions to our system of equations from this row-reduced matrix. So how do we do that? Well, like I said, we have infinite solutions here, so we have to have a free variable. So the first thing we need to do is identify a free variable. So to do that, we go down the columns and see which one doesn't have a leading one, which variable doesn't have a leading one. We go down the column of x1, we see that x1 has a leading one. We go down the column of x2, we see x2 has a leading one, but x3 doesn't have a leading one, so x3 is going to be a free variable. Let's call it t. So x3 is going to equal t, where t is some real number. x1, well, x1 is equal to, well, we're going to have minus 1 over 7 is equal to 0, so we can move that over to that side. So x1 is going to equal 1 over 7t. x2 is going to equal 4 over 7t. And like I said, x3 is just t. So we essentially set our free variable and found the solutions to our system of equations. Now, how do we represent this in terms of our matrix? Because remember, if this was just a system of equations, we'd be done, because these are the solutions to our system of equations, like we've done in the past. But here, this isn't just a system of equations. So it's important that we represent this as a solution to our matrix equation. So here, we could go ahead, and if you remember, our matrix equation was AX is equal to B. So we already know A. A is just a coefficient matrix. I have it right here. So 1, 2, minus 2, 3, 1, minus 2 times x, which is what we were solving for. And if you remember, x was just x1, x2, x3. So I'd have to write out everything that x1, x2, and x3 are equal to. So x1 is going to be 1 over 7t. x2 is going to equal 4 over 7t. And x3 is just going to equal t. So these are the solutions to our system of equations. And this is going to equal b, which we said was 0, 0. So just to recap at the end, because this was a considerable amount of information, it's not difficult. Really, we've done all of this before in the past, so none of this should be new to you, but I just want to recap everything because there was a lot of information here. A is going to be the coefficient matrix of our system of equations. X is going to represent the variables, and B is going to represent the constants to our system of equations. So here we have our X being X1, X2, and X3, our A being the coefficient matrix, which represent the coefficients of our system, and B just representing 0, 0, which are the constants. Using this, we can convert our matrix to row-reduced echelon form by just taking A and adding the column of B, row reducing it, and then obtaining the solutions over here, where we had one free variable in this case, and we can represent the solutions to our matrix equation by substituting in back for x.
I just wanted to thank you for sticking around until the end of the video. It really does mean a lot to me. If you have any questions, you're welcome to leave a comment, and I'll try and respond as quickly as possible. On screen, you should see a link to a playlist containing every single one of my individual linear algebra videos that I made so far, and the ones that I would have made in the future, so go ahead and check that out. You should also see my last video, so if you're a little bit confused in this one and want to see the previous concept, you can click on that. And finally, you should see a subscribe button, and if you want to be notified for my future videos, and also wanted to tell me that you enjoyed this video, you can do that. Okay, cool. So that's it, and until next time, bye!